Okay, part 2, chapter 17. So I've got not blue, not blue, not blue, and blue. Or not blue to the third power times blue. Okay, and not blue is 0.7. So I'm going to do this. I'm going to say it's 0.7 to the third times 0.3. And I'll hit enter and I'll get 0.1029. So 0.1029 is going to be right about there. Okay, so what's the probability I get my first success on the 5th? Okay, so that's going to be, well, what's going to happen on the 1st? Not blue. What's going to happen on the 2nd? Not blue. 3rd? Not blue. 4th? Not blue. 5th? Blue. So I'm going to have not blue. I'm going to have 4 failures, and then I'm going to have success. So 4 failures and then success. I could do this real quick. 0.7 to the 4th times 0.3 equals 0.07203. 0.07203 is here. Okay. So what's the shape of this distribution? It is skewed to the right. No matter where I start, because I'm multiplying the next step by a decimal, I'm going to get a smaller value. And here I'm taking this value, whatever it is, and I'm multiplying it by another decimal. It's always going to get smaller. This distribution is always going to be skewed right. Hence, this statement down here, the probability histogram of a geometric distribution is always skewed to the right. Okay, that makes sense. Now, let's ask ourselves a question here. Say I want to be here at the 9th. How many failures am I going to have? And your answer is, oh, you're going to have 8 failures, and then you're going to have success. So what I would have here, and I'm going to write this, instead of writing blue, or not blue, I'm going to write failure, which is 1 minus p. Okay, I'm going to have 8 of them, and then I'm going to have 1 success. So I've got failure, which is 1 minus the probability of success, the complement of success, 8 times success. Now, we're going to come back to this in just a second. Let's take a look at this statement right here. Because n is not fixed, there could be an infinite number of x values. And what that is saying in relationship to this statement right here is that because I don't have a set number of times I'm going to do this, what I could say is I could find the probability of having my first success on the 132nd pull. Which means how many failures would I have? If I've got 132 pulls, I'd have 131 failures. 131, and then I would have 1, which would make 132. Okay? Granted, that's not likely to happen, and if we do that on a calculator, we're probably going to get a value that's just going to say, the calculator's just going to say it's 0. But realistically, it could happen. Not likely, but it could. And if I went to enough decimal places, I would find the value. So this actually goes on infinitely. I could find the probability of my first success happening on my 1,047th try. Not likely to happen, but you know, it theoretically could, so I could find that. And that's what that statement here said, which was, because n is not fixed, we got to have an infinite number of x values of the value of x. Okay, so let's take this one more step here. Okay, the expected value of a geometric random variable is, expected value is equal to, in this situation, the formula here says that it's 1 over p, which in our situation would be 1 over 0.3, or how long should I expect to have to go until I get my first blue M&M? Oh, I never started this. And that would be 1 over 0.3, which is 3.33. If I did this a bunch of times, it would on average take me 3.33 times, okay? Here's the formula. The formula for a geometric distribution or geometric probability is the probability of x equaling n, the number that you set in there, is equal to 1 minus p to the n minus 1 over p. Holy crap, that sounds confusing. But it's not. Because this statement, 1 minus p to the n minus 1 times p, is exactly this right here. When we said, okay, when n equals 9, when I have my trial set for 9, we said, how many failures am I going to have? Well, if it's going to happen on my 9th, I'm going to have 8 failures. Because this value, or this exponent, is our value, our total number of tries, minus 1. N minus 1. And if I said, okay, what's the probability it's going to happen on my 21st, so n is equal to 21, then what I would have is I would have failures, how many failures? I'd have 21 minus 1, or 20 failures, and then I would have 1 success. And the exponent for this is 1, so 20 plus 1 really is 21. So that formula, even though it looks is really not hard, because we can do this. And here's what you need to think. You don't need to memorize this formula. What you need to do is you need to memorize your common sense and sit there and say, okay, what's going to happen? What happens on my first trial, next trial? How many failures am I going to have? And then when do I have success? Last up here is standard deviation for a geometric random variable is the square root of q over p squared. And q, depending on which book you're looking at and which formula sheet you're looking at, this is saying the square root of q is failure, 1 minus p over p squared. I don't know why this is written as q here. I think I typed this too, and that's what's sad. Okay, but this is failure over success squared. And you'll probably never, ever, ever have to find the standard deviation of that. And it's not on the formula sheet. And this isn't on the formula sheet either. Okay. And then the probability that x is greater than n, the probability of having more than, taking more than 9 tries is the probability of 9 failures. So what this is saying, the probability that your value is greater than, or it takes more than 9 tries to get a blue M&M, is a probability of having 9 failures, which is 1 minus p to the n power. And that's it for the beginning of this. And I don't know where we're at because it is at the timer, but we're going to stop here. And then we're going to come back with the next step. And the next step on this is the binomial distribution, the other part of the Bernoulli family.